In this example, we're going to use the Z-plot to estimate the volume occupied by 2 moles of water at 710 Kelvin and 400 bar, and also nitrogen at 125 Kelvin and 190 bar. The point of the principle of corresponding states is that we can use the general formation of the ideal gas law and apply some correction to it according to the circumstances. So instead of PV over nRT equal to 1, it's equal to some constant Z that's either greater or lesser than 1. Or it can be at 1 too, but that's just less likely. So let's first change the equation to calculate for volume. And we'll remember at this point we need to find Z by using the reduced values for pressure and temperature. So let's start with water. The reduced temperature is going to be the temperature that it's at, 710 Kelvin, divided by its critical temperature, which is 647.126 Kelvin, which gives us a value around 1.1. And the reduced pressure for water will do the same thing. So 400 bar is the circumstances that we find this water in particular, divided by the critical pressure for water, which is 220.55 bar. And that gives us a number somewhere around 1.8. So now that we have these reduced values for temperature and pressure, we take those over to the Z-plot, and now we can use those two values to find a value for Z. So we start on the bottom with the reduced pressure, and we're going to estimate 1.8 looks to be somewhere around here. And we're going to follow it straight up onto the reduced temperature line that corresponds to what we found for this question. So track this straight up. And now we can go across the x-axis to find where we land. And I'm going to call that right around 0.42 is going to be our value for Z for water for this question. Now that we know the value for Z, we can complete the question for water. So the volume of water is going to be 0.42, which we took from the plot, times, and it asks for 2 moles. So our gas constant will be in units of bar liters, which makes the value 8.314 times 10 to the negative 2 bar liter per mole Kelvin. Temperature in this circumstance is 710 Kelvin. Remember that we're using the actual temperature and pressure here, and not the reduced pressure or temperature, and not the critical temperature and pressure. Okay, and the pressure in this case was 400 bar. And so the volume for water that we have is 0.124 liters. And now we do the exact same process for nitrogen. Looking at nitrogen, the reduced temperature, so the actual temperature is 125 Kelvin. The critical temperature is 126.20 Kelvin, which puts us in the neighborhood of 1.0. And the pressure, the reduced pressure, is 190 bar divided by 34.000 bar, which is 5.6. Again, we shift our attention over to the plot, and now for the reduced pressure, we have to look much higher up. So there's 5.6 is somewhere around there, 5.6. For the reduced pressure, and we'll follow this line up until we get to the reduced temperature equals 1 line. Okay, and we follow this line straight up until it strikes that curve. And track it over, and it's going to land just under 70. So let's call it 0.69. And now that we have a value for Z, we can go back. And again, now we have all of the values we need. So the volume for nitrogen is going to be 0.69 times 2 mole times 8.314 times 10 to the negative 2 liter bar per mole Kelvin. The temperature is 125 Kelvin. And all of that is over 190 bar, which gives us a grand total of 7.55 times 10 to the negative 2 liters. Okay, and there's two examples of using the Z-plot in order to calculate volumes based on the principle of corresponding states.